Hello, thank you for being here today. My name is Petit and I will present my paper entitled RRT-Rope, a deterministic shortening approach for fast near-optimal path planning in large-scale uncluttered 2D environments. This work was supported by University of Sherbrooke and supervised by Professor Alexis, Lussier, Desbiens. You can see here a simulation of our algorithm on the left in 3 different indoor environments. It converges much faster to a near optimal path than some other state-of-the-art algorithms. The idea behind this work was motivated by the project of a UAV intended for the mapping of mining stopes, which are large underground cavities that can reach up to 300 meters in height. The real challenge here is the computational time, but we wanted to take advantage of the topology of these uncluttered environments that are 3-ball homotopic. Also, since a mapping drone would likely travel at low velocities, the problem can be considered holonomic. Let's begin with a short review of the existing state-of-the-art path planners that are popular in those environments. I will focus here on sampling methods and more precisely rapidly exploring random trees, because grid methods like A*, for instance, do not scale well with problem dimensions, while potential fields suffer from local minima and oscillations. The only problem with RRT is really the convergence time. We simulated the path cost versus time of RRT and informed RRT star in one of our environments. We can see that those curves converge slowly, whereas we would like to be somewhere there. Various techniques exist to shortcut a path and optimize it in post-processing. One of them is random node pruning, but it is not optimal due to a loss of resolution. Elastic strips is another path shortening algorithm, but it converges slowly since it is meant for online control purposes. The most powerful method is partial shortcut. Basically, you sequentially select 2 random points on the trajectory and connect them. This non-deterministic approach can lead to irrelevant shortcuts for either a portion of path that is already straight or for a portion of path that is intended to be pruned in the future. Besides, for these algorithms, there is no clear point at which you know the process is complete, so it is really up to you to determine if you've converged. I will now present the main idea that allowed us to develop our algorithm. Basically, with an RRT, you could find the yellow path here, for example, if you omit epsilon like you should do for a holonomic problem. Since we are working here in a 3-ball homotopic environment, we know that any path is in the optimal homotopy class. So you don't need to discover a new homotopy to find the blue path, and you should stop the RRT part as soon as you find the first path. The next step is now to find the mapping between the yellow and the blue path. One could do so by making use of the non-collision information you already have thanks to the raycasting check that was performed during the tree construction. Since you know that every point located on a branch is in the free space, you can implement intermediate nodes. Then we developed a deterministic approach for connecting them with a consistent resolution. We also look for straight line segments to avoid irrelevant shortcuts. This is done on a tree constructed with RRT connect without epsilon. By iterating over each node, you know exactly when the process is completed. New branches also have intermediate nodes to keep the same resolution, and we skip one node if we detected a straight line segment. For more details, please have a look at the pseudocode in our paper. Let's talk simulation now. Here are 2 representative stope environments on the left and an indoor building environment on the right used to challenge our algorithm in pillar-like structures. The first experiment was to compare RRT-Rope with other sampling methods without post-processing. The objective is to confirm our hypothesis that we should start as soon as the first path is found. Our method was performed on a path from the green curve at a random time. We observe a constant blue curve with a low standard deviation, which confirms that there is no correlation between the input and the output path quality in those environments. Finally, the gap between the curves indicates that our algorithm yields to better results. To confirm those results, we had to compare our approach to other shortening methods performed after RRT Connect. Here is an error ellipse plot of the simulations for 100 samples for each algorithm. First, as expected, you can see that RRT-Rope in burgundy is the only method with 1 point, while the other results depends on how many iterations you perform. The path cost range is narrower than the others, and the path is shorter or equal. If you look at partial shortcut, which can reach a similar path cost, it is clear that RRT-Rope is much faster. Let's move on to the analysis of the algorithm. I won't go into the full detailed development of the time and spatial complexity and the discussion about completeness and optimality, but I invite you to have a look at our paper if you're interested. Still, I will talk about the algorithm's parametric sensitivity in this part. The parameter we will observe here is the step size, or delta, which is the distance between two consecutive intermediate nodes. It is obvious that for a low value of delta, the path will be smooth, while for a large value of delta, it will be more uneven. Again, I will not go into the details of the calculations that are presented in our paper. However, we have shown that the number of nodes after the optimization process is close to an inverse function of delta. These results have been confirmed here by means of simulations. We observe that the number of path waypoints has a very small standard deviation for a given environment, which again indicates that we are probably close to the same path every time. It is clear that for a smaller delta and therefore a large number of nodes, one would expect a longer computation time. We wanted to measure this computation time to check our intuition. On the first graph, we can see the search time for a first feasible path in blue. Since this curve is constant, we can see that adding intermediate nodes online in the tree does not add any computation time. The post-processing time is shown on the yellow curve, which has a very small standard deviation. This time is therefore very similar regardless of the first path found, for a fixed value of delta, of course. Finally, the total time in red shows a rather steep slope for a very low value of delta. On the following graph, we see the path cost which varies slightly according to delta, but we are talking here about a very small percentage. If we plot the path cost versus the processing time, we can see that there is probably a trade-off to look for. We have chosen not to use Pareto to do this. Instead, we have introduced a cost function that corresponds to the travel time, which is the path cost divided by the cruise velocity plus the computation time. This is the time between the moment the path request is made and the moment the robot will reach its goal position. The objective here is to minimize this function. We have plotted the value of this function in our three environments here. We have standardized it for the sake of readability of the graph, since the speed has a great influence on the travel time, and only the position of the optimal point is of interest to us, while its value does not matter. For a very slow robot, we see that the optimum is on the left. It makes sense to say that it will be in its interest to spend more time calculating the path to gain some travel distance, whereas a fast robot should start as soon as possible, even if it means catching up a few extra meters on its path. We also found that the path cost affects the choice of delta. As this metric is difficult to know in advance, we have plotted here the curves of the optimal delta with the Euclidean distance between the start and the goal point. This metric is easy to compute and allows us to adjust delta in advance. We can see that for long distance, it is more interesting to choose a larger delta. Finally, we notice that our curves are quite flat. For our speed of 1 meter per second, we see that the delta of 0.8 meters is close to the optimum regardless of the environment. You can see here at the top an animation for different delta values with a path found quickly on the left but a bit uneven, and a path found slowly on the right but closer to the optimal path. Finally, to conclude this presentation, we will discuss the limitations and possible perspectives for our approach. As said earlier, we work in environments that are three-ball homotopic and uncluttered. Nevertheless, one can ask how far the algorithm can perform in other situations. One might expect the algorithm to fall into local minima as depicted here on the left. The yellow path would be the first feasible path that we optimize to the blue path, but really the dashed path would be the shortest. Interestingly, in our third environment that was used to challenge the algorithm in a pillar-like structure, the algorithm does not fall in this type of local minima, thanks to the fact that we check the farthest nodes first. So, we have not observed this kind of limitation experimentally. For someone who would like to use the algorithm in a maze structure, for example, an idea would be to use RRT-Rope and informed RRT connect sequentially to escape from local minima while monitoring when the convergence is reached. I would like to remind you that RRT-Rope was not designed for this purpose, and that its great advantage is its computational rapidity in this type of environment. So we would probably like to use another algorithm for a maze environment. To sum up, our approach benefits from a fast time to find the first path thanks to a version of RRT Connect modified to require fewer samples. Thanks to the addition of intermediate nodes, we are able to obtain a uniform resolution and approach optimality. With deterministic node selection, irrelevant shortcuts are avoided to improve efficiency. RRT-Rope is able to find an equal or shorter path than the state-of-the-art methods in a shorter computation time. This concludes our presentation. Thank you for listening. If you have any question, I will be very glad to answer them.